Good morning, all of you. Today we start Organic Chemistry, Volume 3rd, Chapter Synthetic Dyes. Introduction. In our day to day life, we come across many substances which have specific colors. In this unit, we shall discuss what is color, how it is related to the constitution of molecules, what type of color substances called dyes are currently being used to color various articles of our daily use. Color and constitution. Color. When white light falls on substance, then processes make color. If light is totally reflected, the substance appears white. If the light is totally absorbed, the substance appears black. If a certain portion of the light is absorbed and the rest reflected, the substance has the color of the reflected light. If only a single band is absorbed, the substance has complementary color of the absorbed band. If the substance absorbs all visible light except one band which is reflected, the substance will have the color of the reflected band. For example, it is evident from the above table that is a substance absorb blue color, it will appear yellow, which is complementary color of blue. In fact, no substance absorbs a single band and hence no dye has a pure shade. For example, malachite green predominantly reflects green light, but also to small extent it also reflects red, blue, and violet light. It may, however, be noted that substances which appear to be colorless also have been absorption spectra. In case absorption take place in infrared or ultraviolet regions, but not in the visible region of electromagnetic spectrum. Relation between color and constitution. Many theories have been put forward for time to time to correlate color and molecular structure. Some of these are described below. First, Witt theories. In 1876, it was observed by Otto Witt, a German chemist, that intrinsic color of any compound is due to presence of certain group containing multiple bonds. These groups which impart color to a particular compound are called chromophores. And compound containing the chromophoric group is called chromogen. Some important chromogens are nitrosocarbonyl, para-orthoquinoid, benzene, etc. Greater the number of Further, the greater the number of such chromophores, deeper in the color. This is particularly marked when the chromophores are in conjugation with another. For example, as the number of conjugated double bond increases, the color of diphenyls deepens. Second, ethylene 1,3-butadiene and 1,3,5-hexatriene are colorless, but beta carotene has orange red color due to the presence of 11 conjugated double bonds. Oxochromes. Witt also observed that there are certain groups which themselves are not chromophores but deepen the color when introduced into a colored molecule. Such groups are called oxochromes. For example, OH, NH2, NHR, NR2, X, CO2H. Even alkyl group exert weak oxochrome effect. Let us now examine the effect of oxochromes on the intensity of color. Both naphthalene and naphthol are colorless. 1,3-dinitropnaphthalene is pale yellow, but 2,4-dinitro-1-naphthol is orange red. Thus, the presence of oxochromes, that is OH group, has depended the color of 1,3-dinitronaphthalene chromophore from pale yellow to orange red in Meretis yellow. Two other terms which are also commonly used in the connection of dyes, which are bathochromic and hypsochromic groups. Whereas the bathochromic group bring about the deepening, hypsochromic groups bring about the lightening of color. In dye industry, deepening of color means color changes from yellow to orange, orange to red, red to purple, purple to blue, blue to green, and green to black. This is exactly the order of complementary color of the color absorbed. Thus, when we say that the color of one compound is deeper than the other, it simply means that the wavelength of maximum absorption of former is longer than that of the later. This since visible color is complementary color of the absorbed band. Bathochromic groups case red shift, while hypsochromic groups case blue shift. Second, modern theories or electronic theory of color. Two electronic theories have been proposed to explain the origin of the color. These are valence bond theory and molecular orbital theory. The most important difference between VB and MO theory is in that VB theory electrons are deal with in pairs, but in MO theory they can deal with singly. First, valence bond theory. According to VB theory, the electrons pair of molecules in the ground state are in state of oscillation, and when placed in the path of beam of light, they absorb a photon of appropriate energy and get excited. The wavelength of the photon of light absorbed depends upon the energy difference between the ground state and excited state. The smaller is this difference, longer is the wavelength to light absorbed. To illustrate VB theory of color, let us consider a molecule of ethylene which may be regarded as resonance hybrid in the following structures. To a first approximation, ground state is represented predominantly by structure, while excited state is represented by structure too. The energy difference between these two states is very large, and hence a photon of short wavelength is absorbed. In general, it has been shown that resonance among charged structures lower the energy of both the ground as well as the excited state. Charged structures, however, stabilize the excited state more than they do the ground state. Larger the number of electrons involved in resonance, smaller the energy difference between the ground state and excited state. From the above discussion, it follows that more extended conjugation in a molecular, greater is the contribution of the charge structures, smaller is the energy or difference between ground and the excited states. Hence, the longer is the wavelength of absorption. When the wavelength of absorption is long enough to lie in the visible region, we observe color. Further, the presence of both electron donating group and electron withdrawing group at the ends of conjugated system will extend the conjugation by involving the lone pairs of the electrons present on the heteroatom with pi electrons of conjugated system, and will increase the contribution of charge structures towards the resonance hybrid. Steric effects and color. We know that resonance is maximum when the system is completely or almost completely planar. If due to steric hindrance resonance is inhibited, the depth of color will diminish or the compound may even become colorless. Molecular orbital theory. According to MO theory, whenever a molecule absorbs a photon of light, one electron is transferred from bonding orbital to antibonding orbital depending upon the types of electron present in the molecule. Different type of electronic transitions are possible. A transitions in which a bonding sigma electron is excited to an antibonding sigma orbital is called sigma to sigma star transition. In the same way, pi to pi star transition represents the transition of a bonding pi electron to an anti-bonding pi star orbital. An n pi star orbital transition depends the transition of one electron of a lone pair, that is non-bonding pair of electrons, to an anti-bonding pi star orbital. This type of transition occurs in molecules containing double bonds involving heteroatoms. Of all these transitions, only pi to pi star and n to pi star transitions lie in ordinary UV region. Furthermore, pi to pi star transitions are such more intense, and n pi star transition hence responsible for color. Further, the conjugation increases absorption due to pi to pi star transitions get shifted to longer wavelength and ultimately to the visible region, and hence is responsible for color. In ethylene, there are two types of transitions, that is sigma to sigma star and pi to pi star. The longest wavelength band, that is pi to pi star, absorbs at 175 nanometer. Since the band also lies in the far ultraviolet region, therefore has shifted the band to longer wavelength and intensity has greatly increased. This may be explained as follows. A double bonding consists of two pi MOs, one bonding and other anti-bonding. But when we double bond are brought into conjugation for MO are bond. Two of these, that is pi 1 and pi 2, are bonding and the occupied by a pair of electron each, while the other two are antibonding, that is pi 3 star and pi 4 star. Thus it is clear that energy of highest occupied molecular that is HOMO, that is pi 2, increases, while that of the lowest unoccupied molecular orbital LUMO, that is pi 3 starring, decreases. As a result, the energy levels involved in pi to pi star transitions now come closer, and hence lesser amount of energy is needed. In other words, the energy gap between pi 2 and pi 3 star orbitals in 1,3-butadiene is much lower than in corresponding energy gap in pi and pi star orbitals in ethylene, and hence 1,3-butadiene absorbs at a longer wavelength mm, than ethylene. Further, since the energy levels come closer, their interactions in the excited state increases. In a similar way, we can show that when three double bonds are both in conjugation, the energy gap between the HOMO and LUMO becomes still smaller, and the wavelength of pi to pi star absorption band increases, and when it reaches the visible region, color will appear in the compound. For example, in the polyenes, when n is equal to 6, the absorption band occurs in the blue region, and so the compound is yellow. Similarly, beta carotene absorbs in the greenish blue region, and 422 nanometer lambda max is equal to 122, and hence has orange color. Now let us consider benzene. It absorbs at 254 nanometer and is therefore colorless. Similarly, naphthalene and anthracene are colorless. As the number of fused ring increases, the position of absorption approaches the visible region. Thus, naphthalene with 4 linearly fused ring absorbs in the blue region and hence is yellow, with the pentacene with the absorbs orange light in blue. Complementary color. Dyes. A dye is a colored substance which can be applied in solution or dispersion to substance such as textile fibers, paper, leather, hair, fur, plastic material, wax, a cosmetic base, giving it a colored appearance. Conditions which a dye must satisfy: a substance can be used. A substance can be used as dye for textiles only if it satisfies the following conditions. First, it must have a stable color. Second, it must be able to fix itself or capable to being fixed to the fabric from the solution. Third, when fixed, it must be fast to light, resistant to the action of water, soap, detergent, etc. during washing, organic solvent, dry cleaning, etc. Nomenclature. The chemical names of dye are very complicated and hence trade names are more popular. These trade names often include one or more alphabetical letters and a number, whereas the number indicates the shade. Alphabetical letter refer to the color. For example, G for yellow, R for red. Sometimes alphabets may also refer to some specific properties. For example, WE for fast to washing. Sometimes the letter also stands for intensity of color. For example, 6B stands for deep purple, but sometimes these letters may have entirely different meanings. For example, Algerian blue D here, D stands for direct, which means D is a direct dye for cotton. And classification of dyes. First, natural and synthetic dyes. Since early times, man has been trying to extract dyes from the plants for using them to beautify his clothes. Such dyes are known as natural dyes. Two examples of natural dyes known since early times are indigo and alizarin. India has been the main producer and exporter of indigo. However, natural dyes have only limited shades. Hence, nowadays most of the dyes used as synthetic dyes, which can have a variety of shades. Most of these dyes are aromatic compounds obtained from coal tar, hence these are also called coal tar dyes. Classification of dyes based on their constitutions. In this system, dyes are classified on the basis of chemical constitution or the functional group to which the dyes owe their color. Some important classes are azodyes, nitrodyes, nitrosodies, triphenylmethane dyes, anthraquinone dyes, indigoid dyes, phenylphthalein dyes, acridine dyes. Classification of dyes based on their application. The application of a dye on a particular fiber depends on the nature of the both the fiber and the dye. There are 4 different ways in which a dye molecule may be attached to the fiber through first covalent bond, second hydrogen bond, third ionic bond, van der Waals forces. Based upon the methods of application, dye have been classified into 4 following categories. First, acid dyes. The sodium salts of azo dyes containing sulfonic acid and carboxylic acid groups are called acid dyes. These dyes are applied to the fabric from their acid solution and are used to dye wool, silk, nylon, and polyurethane fibers. The affinity of acid dyes for nylon is higher than that of for the other type, since polycaprolactam fibers containing a higher proportion of free amino groups. These do not have affinity for cotton and hence can't be used to dye cotton. Typical example of an acid dyes are orange 1, orange 2, methyl orange, and Congo red. Orange 1 is a versatile dye prepared by the coupling diazotized sulfonylic acid with alpha naphthol. The dye orange 2 is similarly obtained by the Coupling diazotized sulfinic acid with beta-naphthol. The structures and chemistry of methyl orange and cocoa red will be discussed later in this unit. Second, basic dyes. These dyes are salts of the colored bases containing amino groups as oxochromes. These include azo and triphenyl methane dyes in the acid solution. These amino groups form water soluble contains which then react with anionic sites present on the fabric and thus get attached with the modified or reinforced nylons or polyester can be dyed with these dyes. Some common example of this class are aniline yellow, butter yellow, crystadine G and malachite green. Chirosodine G is an orange dye and this is obtained by the coupling benzene diazonium chloride with metaphenylene diamine. It is generally used to dye silk, wool, cotton, leather and paper. Third, direct or substitutive dyes. These are water soluble dyes as the name suggests that are those dyes which can be directly applied to the fabric from an aqueous solution. These are most suitable for fabric which can form hydrogen bonds with dyes. Thus, these are usually used for dyeing cotton, wool, silk, rayon, and nylon. Congo red and Maltese yellow are the two well-known examples of these classes of dyes. Dispersed dyes, they are water insoluble dyes and are applied to the fabric in form of dispersion of a finely divided dye in soap solution in presence of some destabilizing agents such as phenol, cresol, and benzoic acid. These dyes are used to dye synthetic fibers such as nylon, polyester, and polyacrylonitrile fibers. These dyes belong the class of anthraquinone dyes are suitable for dyeing synthetic polyamide fibers. Important example of dispersed dyes are Cleotin fast pink B and Cleotin fast blue B. V. By fiber reactive dyes, these are those dyes which contain a reactive group which combines directly with the hydroxyl or the amino group of fiber because of the formation of permanent chemical bonds between the fiber and the dye. The color of the dyed fabric is fast and has a long life. Cotton, wool, or silk can be dyed with this type of dyes, since which are derivatives of 2,4-dichloro-1,3,5 triazine are important example of fiber reactive dyes. Vi in grain dyes or insoluble azo dyes. These constitute about 60% of the total dyes used. These are obtained by the coupling of phenols, naphthols, acrylamines, aminophenols absorbed on the surface of a fabric with the diazonium salt. As there is only surface absorption of the dye on the fabric, the color is not fast. These dyes can be used to dye cellulose, silk, polyester, nylon, polypropylene, polyurethanes, acrylonitriles and leather. An example of this type of dye is para red. As dyes also finds use in for foodstuffs, cosmetics, drugs, biological strains such as indicators in chemical analysis. However, because of their toxic nature, these dyes are no longer permitted to dye foodstuffs. Seventh, wet dyes. Wet dyes are insoluble in water, hence can't be used directly for dyeing. Therefore, they are first reduced to a soluble colorless form, leucoform, in a large vats with the reducing agent such as alkaline solution of sodium hydrosulfite. Under these alkaline condition, and leucoform develops affinity for cellulose fiber. Therefore, these dyes are mainly used to dye cotton fibers. The cotton fabric to be dyed in soaked in this alkaline solution and then oxidized to in the insoluble colored form by exposure of air or by some oxidizing agents such as chromic acid or perforbic acid. A well-known example of wet dyes is indigo. Indigo Sol O. On the other hand, is readily soluble in water if it has affinity for cellulose and can be rapidly and quantitatively oxidized on fiber and formation of indigo. It is especially suitable for wool. Eighth, mordant dye. These dyes do not dye the fabric directly but require a mordant. This mordant in fact act as a binding agent between the fiber and dye. For acid dyes, metal ion are used as mordant, but But for basic dyes, tannic acid used as mordant. These dyes are primarily used to dye wool. The fabric to be dyed is first soaked in the solution of suitable metal salt, and the soaked fabric is then dipped in the solution of the dye. When insoluble colored complexes called lakes are formed on the fabric. In this way, the metal ions get attached to the fabric, and then dye molecules are linked to the metal ion through covalent and coordinate bonds. The same dye can give lakes of different color depending upon the metal ion used. For example, Algerian give rose red color with aluminium ions, blue color with barium ions, brownish red with chromium ions, violet with magnesium, and red with strontium ions. Chemistry of some important dyes. First, azo dyes. Azo dye constitute the largest class of synthetic dyes. Their chromophore is argon, that is aromatic system, joined to the azo group, and the common oxo groups are NH2, NR2OH, etc. The usual method of preparation